In this video, I'm going to focus on force diagrams. These are also known as free body diagrams. To teach the concept, I'm going to use a basic example at the top right, where a box sits at rest on a horizontal surface. There are three important steps, I feel, for completing a force diagram, the first of which is to identify your object with a dotted circle. So whatever is in the picture that you want to draw your forces for, put a nice circle around it. It helps it to stand out. I know it's pretty obvious when there's only one object in the picture what you're doing your forces for, but in future questions you might have multiple objects or things tied together, and it will be a crucial step. Step 2 is to draw and label force vectors on a dot off to the side. So near the picture, put a dot. This is the free body. It represents whatever is circled in the picture. And by putting your forces on this dot, it just makes it look nicer. It helps the forces to stand out. And by putting the forces on the picture itself, it can be a little cluttered, a little messy, a little harder to grade. On this example, we've got two forces, a normal force upward from the surface, a gravitational force downward from the earth. These are the only two forces present, so we're done with step 2. Step 3 is to write equations in both the x and y dimensions. These are used to explain the motion or lack of motion of the object in each plane, x and y. So imagine we put this dot at the center of an xy grid. We're going to try to write equations in each dimension using our forces, and since there are no horizontal forces, we don't need a horizontal equation. Vertically, we want to write that Fn up equals Fg down to explain why the box is not moving up or down. Let's apply those same steps to another scenario. Here we have a box again at rest on a table, but now we have a hand coming in from above the box and pushing downward. The box remains motionless under these conditions. So we're going to try to draw a force diagram for the box. First thing we want to do is circle our object. We're drawing our forces for the box, not for the table, not for the hand, clearly for the circled object. Our free body is off to the side, and we'll start listing forces that are present. The first that stands out to me is a gravitational force on the object from the earth, pointing downward. Next, we have a normal force on the object from the surface, holding it up. And finally, we've got a force from the pushing hand directed downward as well. These are the only three that are present. Forces that are not present, well, there's no rope or string or chain in this picture, so no tension. This object is not moving relative to the table, so there's no kinetic friction. And because this is a horizontal table, the box is not trying to slide left or right, so there's no static friction keeping it in place. From there, we want to try to write our equations. Horizontally, we have no forces, so there's no need for an equation. Vertically, we want to say that the total forces up equal the total forces down. That would be something that stays at rest. So the normal force upward equals the addition of gravitational force and the hand force down. If the normal force upward were bigger than the two downward forces, the box would accelerate upwards. It would lift off the table, and that wasn't happening. If instead the two downward forces were bigger than the upward force, the box would have crashed through the table, and that wouldn't happen. That didn't happen either. So we want to say that the forces are equal to explain something sitting still. Final example, one for you to try. Here we have a woman trying to push a box to the right. She's pushing as hard as she can, but it's just too heavy. It won't start to move. Can you complete a force diagram for the box while it sits in place? If you want to pause the video and try this yourself, I'll run you through all the steps here in a minute. All right, we circle our box. You see that at the top right. There are 4 forces on this object. Normal force upwards from the surface, gravitational force downward from the earth. The woman pushes straight to the right, and static friction is present to the left. Because this box is trying to move to the right, that's the way it would go if there was no friction. Something has to keep it in place to the left, and that's where static friction comes from. From there, we write our equations. The horizontal forces must be equal to keep it still horizontally, and the vertical forces must be equal to keep it still vertically.